Okay, well then, since a lot of people were interested in this, the question is how to find it. How to find that mathematically. How to find that work. And of course, the guess at this point in this course is that the answer is going to be about an integral, right? We have to use integration. And now I would like to follow that general path of deciding whether the integral is going to be helpful. So what are the two things we have to check before we look into the setup of the integral? Well, I don't remember that as one of the two questions. So one was additivity, yes. So what was that about? Additivity. Speaking of this setup of motion along the path.
The sum of all its parts is equal to the entire function.
So the sum of, so if I subdivide this path into, say, two paths, this one and that one, then what?
The sum is equal to
the sum of these two paths is equal to the total path. Isn't that obvious? Is that what we want to check? That this path plus that path equals the total path. Because that sounds like the fact about the path having nothing to do with the field of forces. Right? So you probably meant something different than checking that these two paths together give the total path.
All the linear components of the path added together.
or the function that.
Well, the work, right? We are interested in work. So if you subdivide the path into two parts, two subpaths, then we expect we are checking, right? That the work done by that field over that path plus the work done over that path is equal to the work done over the total path. Is that true? Because that's exactly what we call additivity there. And that seems to be true. And what's the second property?
Differentiability.
Differentiability, yes. And what is that about? How can we check that? What is it that we have to check?
If you localize the function that you're trying to integrate.
So if I localize, if I zoom in at some point of the path,
It's a linear function.
then it's a linear function. So what is linear function? Well, the path itself looks like a straight line if I zoom in. So that's okay. What about the forces? What can I assume about the forces? What should we expect about the field of forces as I localize? What do I see? Because at this point I see forces changing direction, changing magnitude as I go from point to point. If I zoom in at this point,
you should expect it going one direction, then over the small distance.
so I would expect if the force at that point is like that, right, I would expect all the forces at all the other points going in the same direction. Almost the same direction, right? And having almost the same magnitude. Right? Is that what you normally expect? That as you zoom in, then this force determines what happens in the neighborhood. Okay. So what we are talking about now is a straight motion, linear motion, in the field of forces, which is very, very special. We assume that the force doesn't change at all. Right? We have constant force. So, making that small picture large, we have a straight motion and all the forces are the same. At every point we have the same force. So we linearized the motion, we linearized the field of forces. What is it that we want to check? We want to check that the work depends linearly on something. And that something is going to be the parameter, because we never talked about how we choose the parameter for integration. So far the parameter was somewhat given to you, and at this point it is also given. So we expect to integrate along this interval AB, and that t is going to be our parameter. And what we really want to check now is that this work done by that constant field along this linear path is proportional to the time spent, right, during this linear motion. Is that true? If you move a particle with the constant velocity, right, that's what it means to be linear. So we have constant velocity motion in a very, very simple field. Just for simplicity, we may assume it's gravity field, right? Constant field. Then the question is whether it is true or not that the work done by that field on the particle is proportional to the time spent. The longer you go, the more work you have. If you travel twice as long, the work done by that field is going to be twice as much. Is that true? Well, the work done by this force on this interval isn't it exactly the same as the work done on that interval if the lengths are the same? Well, these two intervals are exactly the same. They're just moved one from the other. And the force is exactly the same, right? Everywhere. So the work during this interval is the same as during that one. And the length of the interval is proportional to the time. So the work is proportional to the time. So that's kind of a vague argument of why we have that differentiability and why the whole thing should work at the end. Of course, we now have to check and try to set up the integral and verify that all the details match.